Welcome back. So if you've seen the previous video, we started talking about this linear ordinary differential equation, epsilon y double prime plus 2y prime plus y equals 0, where again y is the dependent variable depending upon the independent variable x, which we'll take to be a spatial variable that goes from 0 to 1. Subject to the boundary conditions that y at x equals 0 is 0 and y at x equals 1 is 1. And here epsilon, which is the small parameter, is multiplying the highest derivative term, which in this case happens to be the second derivative, y double prime. So in the previous video we solved this equation exactly, and then we looked at its solution as an approximation in powers of epsilon, as a leading order approximation powers on epsilon, and we found that if we plot the solutions in assuming epsilon is positive in the range that goes from x equals 0 to x equals 1, then somewhere around x of order epsilon, the solution sort of rapidly changes to its peak value, and then it decreases to its value at the other boundary, which is at x equals 1, its value is y equals 1, and so it begins at y equals 0, and then over a very thin layer, which we call the boundary layer, so over a very thin layer, by thin we mean something that is a function of epsilon, and we'll talk more about this. So over a thin layer, the solution changes from its value at one of the boundary conditions, which happens to be 0, rapidly to a peak value, and then it sort of decreases over a longer spatial interval to the value that it takes at the other boundary condition. And sometimes this sort of boundary layer is also called the inner solution. So like this is like an inner layer, and this is called an outer region. So let's write that down. So this is sometimes called an outer region, where the function is somewhat slowly varying, and then there is an inner region, which is the boundary layer. Okay, so we got this sort of heuristic plot by looking at, well, the exact solution and then approximating it to leading order in the small parameter epsilon. And now our task is to see how we can apply, or what kind of a perturbative method we can use to solve this equation, and in fact generalize this to higher order linear differential equations, for instance, and also differential equations where, for instance, these coefficients could in principle vary with the independent variable x. So you could have linear differential equations with coefficients that are no longer constants. So let's take this sort of equation as our sort of excuse to talk about a very powerful method, which can be used to solve linear differential equations of any order. The key word is that they should be linear differential equations of any order, which means the highest derivative term could be of any order, where a small parameter epsilon multiplies the highest derivative term, and in general you could have the other coefficients multiplying the other the sort of lower derivative terms. The coefficients multiplying the lower derivative terms could be functions of the independent variable, and this method is called, the particular method we'll be talking about is known as the, let's write it here, it's called the WKB theory. Okay, and this is named after, W stands for Wenzel, who was a German physicist, K for Kramers, who was a Dutch physicist, and B for Brillouin, who was a French physicist. So their initials, basically WKB, constitute the name of the theory, WKB theory. And so if you're like Dutch, you might call it KWB, or if you're French, you might call it BWK and other permutations. But in fact, the English physicist Relay and mathematician Geoffrey also contributed to the development of this theory. So and again, just to recap, it works for linear differential equations. Linear differential equations of any order even with coefficients that are varying, even with variable coefficients. Okay. One of the things about the variable part of the coefficients is that they are in some senses varying slowly with respect to the independent variable. So here we have everything constant. So the coefficient of the y prime term is 2, the coefficient of the y term is 1. So they are just constants and do not depend upon the independent variable x. But in general, we could consider equations of the form, let's say epsilon y to the power some mth derivative plus some coefficient a m minus 1, that could be a function of x, times m minus 1th derivative of y, and so on, equals to 0. So here this is a variable coefficient which depends upon the independent variable x. But when we're applying this method, we are assuming that these coefficients are in some sense varying slowly with space, in this case space x, or with respect to varying slowly with respect to the independent variable x. And the reason why this is somewhat important to keep in mind is because as we'll see shortly, this method involves making an ansatz for the solution, and that ansatz borrows or sort of tries to generalize what we know about linear differential equations with constant coefficients, and sort of it tries to generalize that idea to linear differential equations where the coefficients are not necessarily constant, but they could vary slowly with space. So let's talk about what are the sort of key ideas behind using the WKB theory for any equation of this form, and then we'll try and apply it to this particular equation and see how it works out. So let's work out what the key ideas are. Okay, so the main idea is, as I was stressing before, let's take this linear differential equation and assume that the solution y can be expressed in the form of an exponential to the power of some function of x divided by a delta, which is a function of the small parameter epsilon. Okay, so this needs a little bit of explanation. So first of all, notice that here the exponent of the exponential is some function of x. Now, if these coefficients were constants, if you recall some of a previous discussion, we have been talking about yx as assuming an ansatz of the form e to the power of a linear function of x, s times x, and then we solve for the parameter s, which reduces an equation with constant coefficients, a linear differential equation with constant coefficients, to an algebraic equation, and then we can find out the parameters s, and then as a superposition of, well, if it's a second order equation, we'll find two values for s in general, and then the overall solution is a superposition of those two, the superposition of the two exponentials. So now what we're doing is we're saying that, okay, let these coefficients vary slowly with x, and instead of the exponent being a linear function of x, let's make it some general function of x, s of x, which is again slowly varying. However, we now have the function s of x divided by a parameter delta, which is a function of epsilon. So that's one of the ideas, that we have some function s of x. Maybe let's write it down, where sx is slowly varying function of x. That's one of the points. The other is there is a delta, which is a function of epsilon. So what is this delta? Now, in the example that we are considering, delta is this function which characterizes the thickness of the boundary layer as a function of epsilon. So for instance, delta could be simply epsilon, it could simply scale as epsilon, but it's possible that it's not always linearly scaling with epsilon, but it is some function of epsilon. So for instance, delta epsilon is something that asymptotically is a function of the small parameter epsilon. Now, the WKB theory is actually far more general than just a tool to characterize regions of sharp transition in a solution which is exponentially increasing or decreasing, which happens to be the case in this particular example. So what we mean by that is the WKB theory can actually be used also to characterize solutions which are rapidly oscillating solutions. So for instance, wave solutions where the wavelength could be oscillating very rapidly as a function, or where the wavelength is actually very small and could be a function of the small parameter epsilon. So if the wavelength is very small and is a function of epsilon, it sort of characterizes very rapid oscillations in the solution. So in fact, the WKB theory can be used for so that's one of the points. The other is, let me write it here, that's the ansatz we make, and the other is that if S of x, or let's write it this way. So there could be two different cases. S of x could be real or it could be imaginary. So the function of S of x could be real or imaginary. In the case it's real, we are talking about something which relates to boundary layer theory, and where delta characterizes the thickness of a rapid transition in an exponentially increasing or decreasing solution. So if Sx is real, you'll have something that's exponentially increasing or decreasing over, in particular, over a length scale that's of the order of delta. When Sx is imaginary, then we have something like e to the power of the unit imaginary I times some real function. So Sx, if Sx is imaginary, we can write it as I, the unit imaginary, times some real function, and then this characterizes some oscillatory behavior over where the oscillations are happening over a length scale which is now characterized by the small parameter delta, which is a function of epsilon. So in that sense, WKB theory is far more general than just as a tool to characterize the boundary layer, and we'll try and talk about some examples where wave-like behavior arises and how it could be used. And here, one other point that I should emphasize is that delta is a function of epsilon, and in particular, delta goes to 0 as epsilon goes to 0. So delta also goes to 0. Delta is also a small parameter, so delta also goes to 0 as epsilon goes to 0. Okay, so just to sort of quickly summarize, we make this kind of an ansatz depending upon s, the function of where s is where the exponent now is a function of x. If the exponent is a real function, we are talking about something that captures a boundary layer phenomenon. If Sx is an imaginary function, we are talking more of a wave-like phenomenon. So we take this ansatz and plug it into the linear differential equation we are trying to solve, and then we need to find out two things: S of x and delta as a function of epsilon. We need to figure out both of these things. Both of these are unknown for now. So the idea now is as follows. Maybe get rid of this also. So the idea is as follows, that we'll take S of x, which is a slowly varying function of x, and expand it in a power series in powers of delta. So we write as S of x as summation n goes from 0 to infinity delta to the power of n s n x. Right? So we'll assume that S of x can be expanded in a power series in this form, and in that case, the ansatz that we are making looks like e exponential to the power of, so when n is 0, you have delta to the power of 0 s naught, but there's a 1 over delta in the here appearing here. So the series looks like S naught divided by delta plus, where again S naught, S1, S2 are all functions of x which we need to figure out. We'll have a term S1 plus S2 delta and so on, higher order terms. So in principle this is the ansatz that we are making. Okay, now again this is a series that contains an infinite number of terms. So one of the questions that again arises is, what kind of a series is this and where do we truncate it? And there are two important points here to be noted. The first point is, when we are writing a series of this form, we are assuming that this is the leading order behavior of the series. So if you look at this condition, delta is going to 0 as epsilon is going to 0. So in principle, S naught over delta will be the term which should be very large because it has a delta in the denominator. So this will be the leading order term in the series. And what we are assuming when we are making this kind of an expansion is that S naught divided by delta is, for instance, much greater than S1 in the limit that delta goes to 0. In the same way, we are assuming that this term is much greater than this. So S1 is much greater than S2 delta in the limit that delta goes to 0. And so on for higher order terms. We are assuming term by term that this is much greater than this is much greater than this, and so on and so forth. Okay. Now where do we truncate this series? So notice that this series expansion is in the exponent of an exponential. So let's say we were to truncate this series at a term which is S n delta to the power of n minus 1. Okay. So what this means is that we are making a series expansion of the form yx is e to the power of s naught divided by delta plus s1 dot 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 sn delta to the power of n minus 1. Let's say we were to truncate it here. So the next term that should have appeared, which we are not including, would be of the form s, or let's write it here. So the next term is e to the power of sn plus 1 delta to the power of n, right? So this is an exponential to the power of some terms. So we can split the exponential into products of exponentials and write, or let's just do that actually explicitly. So we can write this as e to the power of s naught divided by delta, e to the power of s1, e to the and dot 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 e to the power of sn delta n minus 1. And the term we are ignoring is this term, e to the power of sn plus 1 delta n. So this is the term we want to ignore. Now if you want to ignore this term, then this term should be something that's of order 1, because this is e to the power of something, and if this is of order 1, then ignoring it will not change our approximation for yx, right? So what we want is that the term that we are ignoring, e to the power of sn plus 1 delta n, should be of order 1, which means that this term, now if you recall the power series expansion of an exponential, e to the power of x is e to the power of x is 1 plus x plus higher order terms. So if you want to approximate this exponential as something that's of order 1, and this is valid when x is much less than 1. So what we want is that the term that we are ignoring, sn plus 1 times delta to the power of n, be much less than 1, because if that's true, then we can approximate e to the power of sn plus 1 as delta n as 1 plus something that's of order sn plus 1 delta n. So that's the other approximation that that's the other sort of criteria we must impose, that in fact let's write this as Sn plus 1 times delta to the power of n be much less than 1. So these are the two conditions that we impose on this series expansion when we are making this ansatz and plugging it into our solution. Okay, so with that, I think in the next part of the series, let's use these ideas to solve the linear second order differential equation we have been working with and see how the whole WKB process works out to be. So see you in the next video. Thanks.